let me introduce backpropagation briefly to you. So you can go and explore this thing in detail if you are interested, or this might be sufficient to understand what backpropagation is. Okay, so in this diagram we can see we are giving some input vector x, and we are getting some output y. Let's say it's a cat and dog classification. So we are giving this cat image serialized as input, or typically cat image features, some histograms or some features will be calculated. Those features will be given as input to input, and we are expecting this output neuron to predict. Let's say cat and dog, then this one cat for cat 1, and this one for dog as 1, and other value being 0. So for finding this weight, what we can do is initialize this weights randomly, like let's say 0.5, 0.3, something like that for all these weights, and give the input, and do a forward propagation. Forward propagation is nothing but this running this model and checking what is the output. So we will give the input here, this values will be calculated here, and again further this summation and non-linearity will be calculated, and here we will get some output. Let's say we got something like 0.3 and 0.2. So what we are expecting is 1 and 0 because we gave a cat image. Now this error value, like expected 1, and here what we got is something like a 0.3 or something, and here some other value. So whatever is the error, we are calculating this difference of this, or basically error we are taking, what is the difference, here also what is the difference, and that error is contributed by all these weights, and then we will calculate the rate of change of that error with respect to the weights, and whichever is having higher value for this rate of change of error with respect to weight, when we calculate whichever basically derivative of weight error with respect to weight, if it is large, that means that weight contributed more into this error. If the derivative is less, that means that weight might be almost okay, or at least neutral. It's not causing any problem, or this error is not caused much by that weight. So whatever is the error value, and thus we can calculate what is the change in weight such that this error is reduced. Basically negative this whatever is the derivative we got, from that we can estimate what is the, like at least whether the weight should be increased or decreased, we can easily estimate. Actually delta wj or delta weight will be calculated based on this error. So its derivation is there in detail. We'll added this link in the PPT, and it is shared, so you can, this is a really good blog. It's explaining in detail how the error is calculated, how the derivative is taken, and all the math is provided here. So basically this chain rule is what crux thing is. So this is that error value we were talking about. So error values, square mean square value is calculated, and that error is what, for that error we are calculating the derivative with respect to the each weight, what is the value of this change in error with respect to change in weight, and that is spread out in this chain rule fashion, and then we can finally estimate or finally derive from this that so yeah, this time you should be knowing this delta is like this dou e, delta e, or that error, rate of change of error with respect to this delta or rate of change of a. A is nothing but the value here, like this sigma xi wi, that summation of multiplication with the weight of the input is what is this a j. For each jth neuron it will be aj, and with what is the rate of change of error with respect to change of rate of change with respect to change in this aj10. So that is what we call it, this delta. So this delta by substituting in this earlier equation, we will come to this equation. So delta Wj equal to minus, this is learning rate. At what rate this weight to be changed is determined by this learning rate, and that we can, something we can choose. It's a constant, this, so change in weight equal to minus the learning rate into rate of change of error with respect to that particular weight. So it is as simple as that. So delta rule adjusts the weight Wj proportional to the sensitivity. This is a basic rule for changing weight, and that can be again calculated. This delta E by delta Wj can be calculated as that earlier delta into xi. So this derivation is there. So that means simply this is the learning rate. This is the rate of change of error with respect to this summation of this xi wi, and then we have to just multiply it with the input xi, whatever it is coming as input. For example, for this weight, and we got some error, then this weight can be adjusted, and that value is delta Wj0 will be equal to minus learning rate, let's say 0.001 typically, or some other value, into this delta Nj, which is rate of change of this Aj with respect to or rate of change of error with respect to this rate of change of Aj, which can be calculated and multiplied by again this input, whatever x0 for this example. So same strategy can be applied into multiple layers as well. So whatever is the error here can be propagated back. So again, there are previous weights are there, and each weight we will calculate again with respect to those weights. What are the what is the change in this error, and so like that we can calculate, or basically that same rule equation we can apply here as well. So again, it will be in this term into again like a similar kind of term will come, and that's how we can calculate the rate of change change in weight required, such that the error here is reduced, and if the error here is reduced and here as well and here reduced, then the error here also will reduce. So whatever is the error that we are getting here is distributed based on that we are calculating weights here, and that error value contribution of this weight to that error is calculated, and that contribution is again distributed back. So as you can see, the more layers we have, that one small error that we got here will get distributed, and again that part of it will get distributed again. So once we have more layers, that contribution of each weight to the error will be very less, and that's what is called this vanishing gradient. Basically that gradient is reducing, and if you are making this learning rate high, so earlier whatever I said when learning rate is less. So if learning rate is kept high, then reverse will happen. So error contribution here, this error, if learning rate is equation, in this equation if learning rate is more, then the contribution error value here will be more than whatever is here, and then again we will calculate the, when we distribute it back here, this error will be even further larger, and soon it will be like above the integer level, or whatever is the numeric value, it will be like a very high value, and then based on that this weight calculation becomes impossible. Values will be too high, or either too high in case of exploding, and either too small in case of vanishing. So that is what limited this network from growing. We can add so typically this is how it will be: input layer, one hidden layer, and output layer. Maximum what we go is 2 hidden layers, and in 2 hidden layer itself we will come to know all these issues. It's very difficult to get some accuracy. So that was the case just few years back. Actually, this was what we were having, like maybe 2010 or before. What we had was this artificial neural network, and this was big stuff even back then, in the sense like it was really cool to use this, but we know the accuracy we can achieve, what this thing can achieve is limited. Actually, this SVM and all were giving even better result than artificial neural network, so to speak, brain mimicking brain. So yeah, and then this good news came, convolutional neural network, and things changed from there. Yeah, we'll see that later.